To solve a linear programming problem, we first assign variables to the unknowns. Second, create an objective function, that is the thing we're trying to maximize and minimize. Part 3, we create the constraints. 4, we graph those constraints. And then 5, plug the vertices of the shaded region into the objective function to maximize it or minimize it. The Student Activities Department of a community college plans to rent buses and vans for a spring break trip. Each bus has 40 regular seats and 1 special seat, designed to accommodate travelers with disabilities. Each van has 8 regular seats and 3 special seats. The rental cost is $350 for each van and $975 for each bus. If 320 regular seats and 36 special seats are required for the trip, how many vehicles of each type should be rented to minimize cost? Step 1, let's label the unknowns. And that is, how many vehicles do we need? So the number of buses and vans. Since we're ultimately going to be doing some graphing, let's use x's and y's. So let's let x be the number of buses, and we can let y be the number of vans. Up next, we'll create the objective function. Z, evaluated at 2 different variables, x and y, is the thing you're trying to maximize or minimize. In this case, we're trying to minimize cost. So we want to go through and find everything that has something to do with cost. We have $350 for vans and $975 for buses. So I'm going to stay in the order that we have the variables in. $975 for each bus, that is x, plus $350 for each van, or y. Next, we'll label the constraints. We need the number of buses to be positive, and we need the number of vans to be positive. We don't want a negative number of vehicles. That wouldn't make sense. Next, we're going to look at the type of seats. First, let's focus on the regular seats. We have 40 for each bus, so that is 40x. And we have 8 regular seats for each van, so that's 8y. And we want at least 320 regular seats. So we're going to make that greater than or equal to 320. Next, we'll focus on the special seats. Each bus has 1 special seat, 1x. Each van has 3 special seats, that is 3y. And we want to have at least 36 special seats, so we need to make that greater than or equal to 36. Our next goal is to graph those constraints. So remember that we're focusing on quadrant 1. And there's a couple different ways to graph those 2 lines. I like to use the intercept method in this case. So we have 40x plus 8y. We're going to change that to an equation, equals 320. In order to find the x-intercept, we make y 0. So this term is just going to go away. We have 40x equals 320. Divide by 40, and we get that x is equal to 8. So we have the coordinate 8, 0. To find the y-intercept, we make x 0. So this term goes away, and we have 8y equals 320. Divide by 8, and y is equal to 40. The coordinate would then be 0, 40. Next, we'll look at the other line. That is x plus 3y equals 36. Again, I'll use the intercept method. To find the x-intercept, we make y 0. So that term goes away, leaving us with x equals 36, or the coordinate 36, 0. To find the y-intercept, we make x 0. So this term goes away, we're left with 3y equals 36. Divide by 3, and y is equal to 12. We now have the coordinate 0, 12. From here, we can sketch those two lines. So I'm going to make my tick marks go up in increments of 4. So we have 4, 8, 12, 16, 20, 24, 28, 32, 36, and 40. Same thing on the y-axis, 4, 8, 12, 16, 20, 24, 28, 32, 36, and 40. Graphing the red line, we have an x-intercept of 8 and a y-intercept of 40. Graphing the green line, we have an x-intercept of 36 and a y-intercept of 12. Now remember that these are actually inequalities, so we need to do some shading. We can pick a test point to determine where to shade. Typically 0, 0 is the easy one to test. If we test 0, 0 in each of these, we get a false statement. 0 is not bigger than 320, and 0 is not bigger than 36. That means we're going to be shading above both of those lines. But keep in mind, we also want to stay restricted to quadrant 1. So we're looking at this shaded region. Our next goal is to look at the vertices of that shaded region and plug them into the objective function that we found at the beginning. The first vertex is somewhat obvious. It is 0, 40. The intersection vertex we don't actually have yet. And then the other vertice we know to be 36, 0. So our next goal is to figure out the intersection point here. We can do that by solving this system of equations. I'm going to use a matrix to do that. We have 40, 8, and 320, 1, 3, 36. Let's throw that into a matrix and reduce the matrix. To do that, we will go to second matrix, go right to edit, hit enter. This is a 2 by 3. Then the entries are 40, 8, 320, 1, 3, and 36. Exit the matrix by hitting the second quit. Then we need to reduce that matrix. Second matrix, go right to math, scroll until we see RREF. Hit enter, and then second matrix again, hit enter, close the parenthesis, enter one more time, and we now get the reduced matrix. 106, 0, 1, 10. So we now have the coordinate of that intersection. That is 6, 10. Finally, we'll plug each of those vertices into the objective function to see which one minimizes the cost. As a reminder, that objective function is z of xy equals 975x plus 350y. The first point we'll test is 0, 40. 975 times 0 plus 350 times 40. 975 times 0 is just 0. So 350 times 40. That is $14,000. Next, we'll plug in 6 10 to the objective function. 975 times 6 plus 350 times 10. And this time we get $9,350. Finally, let's see what happens if we do the other vertex 36, 0. 975 times 36 plus 350 times 0. 975 times 36 is $35,100. So in all three cases, we have enough seats to take every student to the spring break trip. But obviously, we want to go with the cheapest option, $9,350. And that happens when we take 6 buses and 10 vans.